Hello, ma'am.
Hello, sir. Good evening, sir.
Yeah, ma'am. Yeah, ma'am. Can I continue?
Yes, sir. You can continue, sir. I'll make you as a host, sir.
Yeah.
Yeah, sir. You can continue, sir.
Okay, ma'am. Good evening. Can you hear me, Ajay, Tanushree?
Yes, sir. Good evening, sir.
Yeah, good evening. Good evening. Tanushree? Oh, yeah, good evening. All right, we'll continue. Yesterday, last class, we learned about the solutions, different types of solutions, and we learned few problems based on different methods of expressing the concentrations. We'll continue with the topic. Now, colligative properties. What is this colligative property? In order to understand colligative property, we should know something called as a dilute solution. What do you mean by a dilute solution? A solution in which the concentration of the solute is very, very less compared to the concentration of the solvent is called as dilute solution. A solution whose concentration is very low is called as dilute solution, or the concentration of the solute is very, very less compared to the volume of the solvent, or concentration of the solvent will be called as a dilute solution. Now, for an example, if I take 1 molar HCl, and if I take 0.001 molar HCl, I can call 0.001 molar HCl to be what? A dilute solution, because the concentration of HCl is very less. Now, this colligative property is associated with dilute solutions. That is why we have to understand what is dilute solution. Before we get into the definition of a colligative property, we should understand all the colligative property will have an analogy, similarity, like was, or with what? A gas. It will have an analogy with what? A gas. Now, in gases, what happens? The molecules are free to move. Molecules are very free to move because there is no force of attraction between what? The gas molecules. That is why the gas molecules are free to move. Now, when I'm talking about a dilute solution, if I consider this to be a dilute solution, this is dilute solution. This is a solvent. And we will consider the solute particles like this. Solute particles are very few now. Only few solute particles I'm representing. Now, since the solvent is more, or the volume of the solvent is very high compared to the solute particles, will not the solute particles move freely like gas? Will not the solute particle move freely like gas? Tell me. The volume available for the particles to move is more. Therefore, these particles will have will be free to move like what? Gas. Yes or no?
Yes, sir.
That is why we said all this colligative property has an analogy or similarity with the behavior of what? A gas. Now, in dilute solution, you can observe that what I've written the solvent, the blue lines in excess, and the solute particles I've written only few. That means the solute particle concentration is very, very less considered to the concentration of the solvent. Those kind of solutions are called as dilute solution. A solution whose concentration is very, very less is called as a dilute solution. Now, what is this colligative property? It's a certain property of a dilute solution. The condition for us to understand colligative properties, the solution should be dilute. A certain property of a dilute solution containing non-volatile solute. What do you mean by non-volatile solute? A solute should not vaporize. The solute should not undergo evaporation. All right. So certain property of a dilute solution containing non-volatile solute do not depend on the nature of the solute dissolved, but depends only on the concentration. That is the number of particles of the solute present in a solution. Such properties are called as colligative property. Now, what is this colligative property? It's a lengthy definition. We'll make it very simple. What is colligative property? Now, I'll write here the simple definition. I will write so that you can understand better. Now, what is this colligative property? It's a property of a dilute solution. Property of a dilute solution, which depends only on the number of solute particles, which depends only on the number of solute particles and not on the nature. Not on the nature. Those kind of properties are called as colligative property. See, it's a property of a dilute solution which depends only on the number of solute particles and not on the nature of the solute particles. When we say not on the nature, it does not depend on the size, shape, or reactivity, all that. It depends only on the number, whether I have 10 particles to 20 particles, that number of the solute particles. So any property which depends only on the number of solute particles, not on the nature of the solute particle, those properties are called as colligative property. What is colligative property? Give some examples. They can ask you, what is colligative property? It is a property of a dilute solution. See, colligative property is not applicable for a concentrated solution. In concentrated solution, the particles will be close to each other, solute particles. It will not be free to move like gas. Therefore, concentrated solution is not accepted or not dealt to learn the colligative properties. It's only a dilute solution which we'll be using in order to learn the colligative property. So property of a dilute solution which depends only on the number of solute particles and not on the nature of the solute particles. Those are called as colligative property. Is it clear with this definition? Is it clear? Are you people there? Yeah.
Yes, sir.
Yeah. Why so long to answer? So it's a property of a dilute solution which depends on the number of solute particles, not on the nature. Those kind of properties are called as colligative properties. So we have 4 colligative property. What's the purpose of learning colligative property? The purpose of learning colligative property is we can find the molecular weight of non-volatile solutes. Non-volatile solutes. So this colligative property can be used to determine or find the molecular weights of the non-volatile solute. That is one of the applications of colligative property. Now, what are the 4 colligative properties we have? The first one is lowering of vapor pressure of solvent. Lowering of vapor pressure of solvent. Next is osmotic pressure of the solution. Third is elevation in boiling point. This elevation in boiling point is also called as increase in boiling point. It is also called as increase in boiling point. It is also called as eubilioscopy. It is also called as eubilioscopy. Now, depression and freezing point. We will learn what is all this property a little later. Depression is also represented by a decrease. It is called as cryoscopy. It's otherwise called as cryoscopy. Depression in freezing point is called as cryoscopy, or decrease in freezing point is also called as cryoscopy. Elevation in boiling point is called as eubilioscopy. Now, we have something called as osmotic pressure of the solution, and the first one we're going to learn is called as lowering of vapor pressure of the solvent. Lowering of vapor pressure of the solvent. I have to give you the mathematical representation. We will learn the mathematical representation in a few minutes' time. Now, I hope that you understood what is colligative properties and how many types of colligative properties are there. 4 types. One is relative lowering or lowering of vapor pressure. Next is osmotic pressure. Third is elevation in boiling point. And the 4th is depression in freezing point. Elevation in boiling point is called as eubilioscopy. Depression in freezing point is called as cryoscopy. Now see here, since colligative property depends upon the number of solute particles present in the solution, the simple case will be that when the solute is a non-electrolyte. What do you mean by an electrolyte and a non-electrolyte? What is an electrolyte and a non-electrolyte? What is an electrolyte and a non-electrolyte? What's that different? What's that? Give an example at least for an electrolyte and non-electrolyte.
So,
Yeah.
so electrolyte will be acidified water, sir. Non-electrolyte, pure water.
Pure water. All right, that's an example. It's fine. Can you define what is an electrolyte and a non-electrolyte?
So, an electrolyte is a substance which can conduct electricity in the liquid or molten state, sir.
Okay. Correct. Which
And
can conduct
normal,
electricity will be called as an electrolyte, and which do not conduct electricity or which does not conduct electricity will be called as non-electrolyte. All right. Now, generally conduct electricity. Okay. Generally, when we say electrolyte will be ionic in nature. You are right. Okay. Generally, electrolyte will be ionic in nature. Now, for an example, NaCl we can take. This will have Na plus and Cl minus. It will undergo ionization. So therefore, these ions will be in a position to conduct electricity, move, and therefore it can conduct electricity. Now, when we take non-electrolyte for an example, if we take glucose, C6H12O6, glucose, if you put into water, glucose will dissolve, but the glucose will not dissociate to give ions. Glucose molecule will remain as such in the solution state. Since ions are not formed by glucose, glucose will be an example for what? Non-electrolyte. So generally, electrolytes are ionic in nature, non-electrolytes are covalent in nature. All right, covalent bonding. You know what is ionic bonding and covalent bonding. So we're not going to talk about the bonding part now. So you should remember, non-electrolyte means does not conduct electricity. Now, since the property depends upon the number of solute particles present in the solution, the simple case will be that when the solute is a non-electrolyte. In case the solute is an electrolyte, it may split to a number of ions. See, NaCl can split to Na plus and Cl minus. So, non-electrolyte does not undergo ionization, does not split. So, but in case of electrolyte, it may split to a number of ions, each of which can act as a particle. So here, we were talking about NaCl, but NaCl when dissolved in water, NaCl as we talk about is a one molecule. But when we dissolve it in water, what happens? It dissociates to form, splits to form Na plus and Cl minus. So this Na plus will behave like a particle, Cl minus will behave like a particle. But in case of glucose, since it does not undergo splitting, how many number of glucose molecules are dissolving? Those many number of glucose molecules will be present in the solution. Did you follow? Because it does not undergo what? Splitting. It does not undergo dissociation. Followed? Followed?
yes, sir.
Yeah. I did something. Yeah. Okay. Now, that's why we are talking with respect to non-electrolyte. Now, each colligative property is exactly related to other. So, each colligative property will be related to each other. Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point are directly proportional to osmotic pressure. How each colligative property is related? Lowering of vapor pressure, elevation in boiling point, depression in freezing point, all three are directly proportional to osmotic pressure. Osmotic pressure. I'll give the mathematical representation of, giving the representation for all this in the next few minutes. All right. So this is with respect to introduction to colligative property. Now the first property what we're talking about is vapor pressure, lowering of vapor pressure. Now, firstly, you tell me what is vapor pressure? Anybody? What is vapor pressure?
So,
Hmm.
sir, I'm not sure, sir, but is vapor pressure exerted by the water vapor in the atmosphere on the Earth's surface?
All right. That's partially right. Anyways, we will understand that vapor pressure in detail now. I will take a solvent, not only water, it can be any solvent. I take a solvent here. In a container, I've taken a solvent. Now, this solvent will have the tendency to vaporize. Now, water, at what temperature water will vaporize? At what temperature water vaporize? At what temperature water will vaporize?
Sir,
Hmm.
so 100 degrees Celsius.
100 degree Celsius. Then how rain is formed? How rain is formed?
Sir, when the water is cooled back down, sir, on reaching the Earth's
No.
atmosphere.
Yeah. Now, how does it reach Earth's atmosphere? Firstly, how does it reach Earth's atmosphere? Someone is boiling at 100 degrees. Is anybody boiling the water at 100 degrees in the sea
No,
or
sir.
in the...
No,
No,
sir.
then how? So water has a tendency to vaporize even in the room temperature. Water has a tendency to vaporize at even room temperature. So when this water vaporizes at room temperature, what happens? Now assume this is water vapors. This is nothing but water vapors. Now assume there is a cool breeze which blows across. Cool breeze blows across. What happens? Now this water vapors will, what happens? This water vapors will condense back. Now when this water vapors will condense back, now are you able to understand there is an equilibrium established between the water vapors and the water? Can you observe that? There's an equilibrium between what? Water vapors and water. So at this equilibrium, the pressure exerted by these, pressure exerted by the vapors when they are in contact with the liquid, at equilibrium is called as vapor pressure. What's the definition for vapor pressure? Pressure exerted by the vapors. Pressure exerted by the vapors when the vapors are in contact with what? Liquid at equilibrium. See, these are water vapors. These water vapors are in contact with water at equilibrium. At that time, whatever the pressure exerted by these vapors, they are called as vapor pressure. They are called as what? They're called as
It's a
what?
vapor
Vapor?
pressure.
Yes.
Vapor.
No issues with this? So far you understood? Okay.
Yes, sir.
Now we'll continue with this. Now this is with respect to pure water. So you can take any solvent. Any solvent you can take. You can take benzene, you can take chloroform, you can take carbon tetrachloride, you can take alcohol, anything. So anything, any liquid for that matter, it will vaporize even at room temperature to a little extent. And they will establish an equilibrium between the vapors and that liquid. That time, whatever the pressure, vapor pressure you measure, that will be called as the vapor pressure of the liquid. Now, the same condition. Now, what we are doing is we are taking a beaker, same volume of liquid I'm taking. It can be water. All right. Now, what we are doing is we are adding some glucose molecules, non-electrolyte glucose we're adding. When I add some glucose, what happens? Now the glucose particles will dissolve. Yes or no? Glucose particle will dissolve in the solution like this. Yes? Yes or no?
Yes, sir.
Yes. Now you tell me this water will start vaporizing even at room temperature and there will be water vapors formed. And when a cool breeze again blows that side, what we understand that the water will undergo condensation. Right. Now you tell me this pressure what we measure is also called as vapor pressure. Now my question is, pure water we have taken, we have measured the vapor pressure to be, maybe we will mark the vapor pressure to be A. We'll mark the vapor pressure of the pure water to be A, and we will mark the vapor pressure of the solution B what? For the solution, this is, since we are adding glucose, it becomes a solution, remember, is B. Now tell me, vapor pressure of A will be more or B will be more, or it will be same? Tell me. Vapor pressure of A, pure water will be more, or of the solution will be more, or it will be equal? You can tell me, no problem.
So, so the vapor pressure of the solution will be more, sir.
Solution will be more. Now, vapor pressure of the pure solvent, water, in this case, will be greater. Why? Now, when I add glucose, you can see on the surface, some of the water molecules is replaced by glucose. That means the concentration of the solvent on the surface decreases in case of solution. Therefore, instead of getting more water molecule vaporized, only less amount of water will get vaporized. Glucose will not vaporize, no? Glucose will remain here only. So only less amount of water molecule will vaporize. Therefore, what happens? The vapor pressure of the solution is always less than the vapor pressure of a solvent. You have to note this. Vapor pressure of solution is always less than vapor pressure of the pure solvent. Any solvent for that matter. We have taken water as an example, but it can be any solvent. Did you understand what is vapor pressure? And how vapor pressure of the solution and pure solvent is related?
Yes, sir. Yes, sir.
Vapor pressure of a solution is lesser than the vapor pressure of the solvent. I explained the reason also. Now, the first colligative property we are learning. The first colligative property is lowering of vapor pressure. Lowering of vapor pressure. Now, always remember, vapor pressure of a pure solvent is represented as P naught. And vapor pressure of a solution is represented by P. So you should remember always that P is less than P naught. That means vapor pressure of a solution is less than the vapor pressure of a pure solvent. This is the representation. P is less than what? P naught. Now, what is this lowering of vapor pressure? The pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature is called as vapor pressure. I explained this. Vapor pressure of liquid depends upon. We will learn the reasons. Now, you understood what is vapor pressure. Vapor pressure is nothing but the pressure exerted by the vapors when the liquid, above the liquid surface in equilibrium with the liquid at given temperature. I clearly explained and wrote it here. Pressure exerted by the vapors when the vapors are in contact with the liquid at equilibrium. I wrote it clearly. So this is vapor pressure definition. And vapor pressure depends on the following. First one is nature of the liquid. Liquid which have weak intermolecular force of attraction are volatile and have great vapor pressure. So in the liquid, if the intermolecular force of attraction is less, then the escaping tendency will be more. They will be more volatile. Therefore, it will give what? More vapor pressure. For example, dimethyl ether has greater vapor pressure than alcohol. In alcohol, hydrogen bonding will be there. In alcohol, hydrogen bonding. Each alcohol molecules will be bound by a hydrogen bond. Therefore, it cannot escape. But in case of dimethyl ether, there is no hydrogen bonding. Therefore, these molecules are very free. It vaporizes easily compared to alcohol. Therefore, dimethyl ether has greater vapor pressure than ethanol. The first one is nature of the liquid. The second factor is temperature. As temperature increases, vapor pressure also increases. So we can write vapor pressure is directly proportional to temperature. Because the reason to this is due to the reason that with increase in temperature, more molecules of the liquid can go into vapor phase. So as that, see, if you boil water, vapors are more compared to water which is not boiled. All right. So when you increase the temperature, vapor pressure increases. That's a natural phenomenon. Next is purity of the liquid. Pure liquid always has vapor pressure greater than its solution. Pure liquid has vapor pressure greater than its solution. I explained it in the previous slide. I wrote it as P is inversely proportional. P is what? Less than what? P naught. Or we can write that as P is greater than P. P naught is greater than P. It's both are same. Both are same. Yes. Followed or not?
Yes, sir.
Yeah. Now, coming to the lowering of vapor pressure, we need to learn a law called as Raoult's law. See, all this will be important for your regular exam as well as competitive exam. That's why I'm taking time to teach you all this. All right, you have to pay attention. Now, coming to Raoult's law. What is this Raoult's law? When a non-volatile substance is dissolved in a liquid, the vapor pressure of the liquid is lowered. See, when a non-volatile substance is dissolved in the liquid, the vapor pressure of the liquid is lowered. I clearly told you with this illustration. This is the vapor pressure of water. I wrote it as P naught. And when you add some glucose, it becomes a solution. For the solution, I told you vapor pressure is less. So whenever a non-volatile solute is added into a solvent, what happens? The vapor pressure decreases or vapor pressure is lowered. They say vapor pressure is lowered. According to Raoult's law in 1887, at any given temperature, the partial vapor pressure P of any component of solution is equal to mole fraction multiplied by the vapor pressure of its component in pure state, that's P naught. See, vapor pressure of any solution. See, at a given temperature, the vapor pressure P of any component of the solution, is equal to, they have taken PA for our understanding. PA is equal to P naught A. What do you mean by P naught A? P naught A is nothing but the vapor pressure of a pure component A. I'll give you an example. Into mole fraction of A. You know how to calculate mole fraction. I will not be taking time to explain mole fraction in detail when we work out the problem. Now just observe what is Raoult's law. Now assume that I have taken water. This is water. And to this, we have added glucose. We will take glucose only. Glucose. So now what happens? Water plus glucose, it becomes a solution. This becomes what? A solution. Now, the vapor pressure of water I have to calculate. So what is the vapor pressure of water now? The vapor pressure of water will be, I can write it as vapor pressure of water will be equal to, see, this is a component. Now, what is the vapor pressure of water in the pure state? So that is P naught into the mole fraction of water. That is called as Raoult's law. That's called as what? Raoult's law. So Raoult's law states that at given temperature, the vapor pressure of any of the component will be equal to the product of mole fraction into vapor pressure of its component in what state? Pure state. That's called as what? Raoult's law. That's called as Raoult's law. The vapor pressure of the solution, total vapor pressure, is a sum of the partial pressure of the components. That is, for solution of two volatile liquids, and the vapor pressure is PA and PB. So total pressure will be equal to PA plus PB. So what is PA? We learned it as P naught into XA. What is PB? P naught into XB. We can write PB as P naught into XB. Did you follow this representation, mathematical representation? Did you follow this? Yeah, you tell me, someone tell me, how do we calculate the mole fraction? How do you calculate the mole fraction? What's the formula to calculate the mole fraction of a solute? If I represent it as B, number of moles of solute divided by number of moles of solvent plus number of moles of solute. Now, likewise, mole fraction of solvent, how do I calculate? Number of moles of solvent divided by number of moles of solvent into number of moles of solute. So, number of moles of a particular component divided by total number of moles of solution. That will be giving you what? Mole fraction of the particular component. Now, alternative, how do you define Raoult's law? Alternative. It may be stated relative lowering of vapor pressure of a solution containing a non-volatile solute is equal to the mole fraction of the solute. See, in two ways we can define. The first one is the vapor pressure of any component of a solution is equal to its mole fraction multiplied by its vapor pressure in pure state. This is one way. The alternative way to define Raoult's law is relative lowering of vapor pressure is of a solution containing non-volatile solute is equal to mole fraction of the solute. in its solution. Mole fraction of its solute in its solution. Relative lowering of vapor pressure is defined as a ratio of lowering of vapor pressure to the vapor pressure of pure solvent. It is determined by Ostwald-Walker's method. We will learn Ostwald-Walker's method a little later. That experimental procedure you do not have in your syllabus. You need to know only the mathematical representation. I will teach you that a little later. Now we will try to understand what is relative lowering of vapor pressure. How do we represent vapor pressure of a pure component? Pure component, pure solvent. What's the vapor pressure of a pure solvent? P naught. Vapor pressure of its solution. Vapor pressure of solution is represented by what? P. Then we know P naught is greater than P. Yes or no? We know that P naught is greater than P. Vapor pressure of a pure component is greater than the vapor pressure of its solution. Yes or no?
Yes, sir.
Now, if that's the case, what's the lowering of vapor pressure? Lowering of vapor pressure is equal to vapor pressure of a pure component minus vapor pressure of its solution. Because we know that P naught is greater than P. So therefore, lowering of vapor pressure is equal to P naught minus P. Now we have relative lowering of vapor pressure. What is this relative lowering of vapor pressure? Relative lowering of vapor pressure is the ratio of lowering of vapor pressure to vapor pressure of a pure solvent. So this is relative lowering of vapor pressure. P naught minus P divided by P naught is called as relative lowering of vapor pressure. Just see here, the relative lowering of vapor pressure of a solution containing a non-volatile solute is equal to mole fraction. I'll come to this. Now, what is the relative lowering of vapor pressure? It's defined that it's a ratio of lowering of vapor pressure to the vapor pressure of pure solvent. See, P naught minus P is what? Lowering of vapor pressure. Divided by vapor pressure of a pure solvent. P naught gives you what? Relative lowering of vapor pressure. Followed this? If that's the case, maybe I can write P naught minus P divided by P naught is equal to NB divided by NA plus NB. What is this NB? What is this NB? Number of moles of solute. NA is number of moles of solvent. See, now the statement you see, the relative lowering of vapor pressure of a solution containing a non-volatile solute is equal to mole fraction of the solute in a solution. So NB is mole fraction, is the number of moles of solute. NA is the number of moles of solvent, and NB is the number of moles of solute. So this is nothing but mole fraction of a solute. So we can represent otherwise P naught minus P divided by P naught is equal to mole fraction of solute XP. Did you understand this relative lowering of vapor pressure? Yeah?
Yes, sir.
Now see the mathematical representation I've given you. The derivation we can do, but it's not worth doing because nobody will ask you the derivation in the exam nor in the competitive exam. See, relative lowering of vapor pressure, according to Raoult's law, P naught is the vapor pressure of pure solvent. They have given PS here. They are represented as PS. PS stands for vapor pressure of its solution, and P naught is the vapor pressure of solvent. This is nothing but relative lowering of vapor pressure. That's equal to mole fraction. I have taken example as NB divided by NA plus NB. Here N2 they have taken. Here N2 is nothing but number of moles of solute. Instead of taking NB, they have represented as what? N1 and N2. N2 is number of moles of solute. N1 is number of moles of solvent. And N2 is number of moles of solute. So this is nothing but mole fraction of the solute. That is what X2 they have given. That is what they are given as X2. Did you understand Raoult's law? The first colligative property we are finishing. We'll have to work out some problems. All right,
Yes.
Let's see how we can go about the problems. Now coming to limitations of Raoult's law. See, Raoult's law is applicable only to dilute solution, not only Raoult's law. Colligative property as such is applicable only to dilute solutions. Any colligative property. Raoult's law is applicable to solution containing non-volatile solute. like glucose, etc. Goes on. Raoult's law is not applicable for solute which dissociate or associate in a particular solution. So that means NaCl we cannot use because it will dissociate to form Na plus and Cl minus. Acetic acid we cannot use because this acetic acid will associate. That means acetic acid will combine with each other. Here it will dissociate. So therefore we cannot use this. But in case of glucose molecule neither undergo dissociation nor they undergo association. Therefore, glucose can be used to study the Raoult's law. All right. So these are the limitations of Raoult's law. Raoult's law is applicable only for dilute solution. The second one is Raoult's law is applicable to solution containing a non-volatile solute, and Raoult's law is not applicable to solute which dissociate or associate in a particular solution. So this is with respect to Raoult's law. Are you ready to work some questions based on this? Ready to work some questions based on this? The aqueous solution of glucose is one or two questions. I don't know how many questions we can work today. Let's see. Is it clear with the relative lowering of vapor pressure? Is it clear? Is it clear? Yeah. Now we'll work out some problems. We'll try to solve lengthy problems, but these kind of problems will be there in your exam without fail. An aqueous solution of glucose is made by dissolving 10 grams of glucose in 90 grams of water. 10 grams of glucose in 90 grams of water at 303 Kelvin. If the vapor pressure of pure water at 303 Kelvin is 32.8 millimeters of mercury, what would be the vapor pressure of its solution? What would be the vapor pressure of its solution? Now, in order to understand, see what is given. It is very simple problem. Given, they have given weight of glucose is 10 grams. Now they've given weight of water. They've given 90 grams. Temperature, we don't want. They've given vapor pressure of pure water. That means they have given P naught. They've given P naught to be 32.8 millimeters of mercury. And they're asking you to calculate P. What is the vapor pressure of its solution? That's what they're asking you to calculate. Now, in order to understand this, we know the formula. Vapor pressure of a solution is equal to vapor pressure of a particular component is equal to partial vapor pressure of a particular component is equal to vapor pressure of that component at pure state into mole fraction of that component, Now, in order to work out this, now they're asking what is the vapor pressure of the solution. So we need to know how to calculate number of moles of glucose. Number of moles of glucose. They've given you 10 grams of glucose and weight in grams divided by molecular mass. Molecular mass of glucose 180. Remember, 10 divided by 180, it is 0.0556 moles. Similarly, number of moles of water. Number of moles of water. They have given 90 grams of water. 90 divided by the molecular mass of water is 18. It will be 5 moles. It will be 5 moles. Now tell me what is the, therefore I can write mole fraction of water. What will be the mole fraction of water? You tell me, anybody? Number of moles of water, it's 5 divided by number of moles of water plus number of moles of glucose in this case. So total number of moles of the solution. So simplifying this, you will get the value 0.989. This is the mole fraction of water. This is the mole fraction of water. What is the question they're asking? What would be the vapor pressure of the solution? Therefore, we can write the vapor pressure of the solution will be equal to, that is PA, that will be equal to P naught of A into XA. What is the P naught of A? They have given P naught of A to be 32.8. Pure vapor pressure of pure water, they have given 32.8. Into what's the mole fraction? We calculated, just now we calculated as 0.989. On simplification, you will get 32.44 millimeters of mercury. So therefore, the answer for this question is option B. Did you follow this problem? Did you follow this problem?
Yes, sir.
Excuse me. The next problem. 1 mole of heptane, vapor pressure is 92 millimeters of mercury, and 4 moles of octane, vapor pressure is 31 millimeters of mercury, form an ideal solution. We will learn what is ideal solution later stages. Find out the vapor pressure of the solution. Now, 1 mole of heptane and 4 moles of octane. So therefore, total number of moles will be equal to 1 plus 4, that is 5. Now, what is the mole fraction of heptane? Mole fraction of heptane. Mole fraction of heptane will be equal to 1 divided by 5. Total, no? 1 divided by 5. We'll keep it as such. Now, what's the mole fraction of octane? Mole fraction of number of moles of octane is 4 divided by total number of moles is what? 4 by 5. Now, what is the vapor pressure of the solution? Vapor pressure of the solution is P naught A into XA plus P naught of B into XB, because two solutions are there, heptane and octane. So therefore, sum of these will give you the total pressure. So P naught of A is how much? P naught of A, heptane, they've given 92. 92 into what's the mole fraction of heptane? 1 by 5 plus for octane, they've given 31. 31 into mole fraction is 4 by 5. On simplification, you will get 43.2 millimeters of mercury. So answer for this question is option B. Did you follow this problem? Excuse me.
Yes, sir.
Yes. Now, next problem. See, these all are wonderful to work. You need to practice. Otherwise, it will be difficult. So practice. The next problem. The vapor pressure of chloroform and dichloromethane at 298 Kelvin is 200 millimeters of mercury and 415 millimeters of mercury, respectively. What is the mole fraction of each component? And calculate the vapor pressure of the solution prepared by mixing 25.5 grams of chloroform and 40 grams of dichloromethane at 298 Kelvin. Now, what is the molecular mass of chloroform? Molecular mass of chloroform, CHCl3. Carbon is 12, hydrogen is 1, chlorine is 35.5. So into 3, that will give you 119.5 gram per mole. So what's the molecular weight of dichloromethane, CH2Cl2? So carbon is 12, hydrogen is 2 into 1, 2, and chlorine is 35.5 into 2. So multiplication of all this, you will get 85 gram per mole, molecular mass. Now, what is the number of moles? Number of moles of chloroform, CHCl3. They have given, see in this question, they've given 25.5 grams. So 25.5 grams divided by, what's the molecular mass of chloroform? It is 119.5. So that will give you 0.213. That's the number of moles of chloroform. So number of moles of dichloromethane, CH2Cl2. They've given 40 grams. And what's the molecular mass? 85. So this will be around 0.470 moles. 0.470 moles. I hope that you followed. Yes. Therefore, we can write total number of moles. Total number of moles will be what? 0.213 plus 0.474. That will be equal to 0.683 moles. So total number of moles will be 0.683 moles. Now you tell me, what is the question they've asked? They've asked the question to calculate mole fraction of each component. So the first one will be mole fraction of chloroform, CHCl3. What is the number of moles of chloroform? It is 0.213. 0.213. Total number of moles is how much? 0.683. So on simplification, you will get it as 0.31. Similarly, what is the mole fraction? Sorry, mole fraction of dichloromethane, CH2Cl2. It is 0.474 divided by 0.683. On simplification, you will get it as 0.688. 0.688. On simplification, I think you should get it on 0.688. Check whether the simplification is right. It should be right, 0.688. Now tell me the second part of the question. See, we got it here. Here's the answer we got. 0.312 mole fraction of chloroform and 0.688 mole fraction of dichloromethane. The last part of the topic we will work that they've asked. What is that they've asked? They've asked you to calculate the vapor pressure of the solution prepared by mixing this. What will be the vapor pressure of the solution? We know the vapor pressure of the solution will be pure component into mole fraction of the component A plus vapor pressure of a pure component into mole fraction of B. So what is that they've given you? The question they've given you, vapor pressure pure component is chloroform is 200 and for dichloromethane is 450. So it will be 200 into what is XA? What is the mole fraction of chloroform? It is 0.312 plus what is B? 400 they've given, and what's the mole fraction of dichloromethane? Now we calculate 0.688. On simplification, you will get as 347.92 millimeters of mercury. You can work this and check. Okay, so it will be 342.927 millimeters of mercury. Therefore, the answer for this question is option A. I will just reduce the size and you check whether you follow with this. If you have any clarification, you can ask, or else we'll continue with a few more problems. Is that clear? Is that clear?
Yes, sir.
Yeah. The next question is, vapor pressure of benzene at 90 degrees is 1020 torr. Torr is also a method of expressing the vapor pressure. All right. A solution of 5 grams of solute in 58.5 grams of benzene has vapor pressure 990 torr, the molecular weight of the substance. So this I didn't teach you, but anyways, we'll understand. Vapor pressure of a pure solvent divided by vapor pressure of a solution divided by vapor pressure of pure solvent. This is called as relative lowering of vapor pressure. This relative lowering of vapor pressure will be equal to W into capital M divided by small letter m into capital W. They have represented it like this. So vapor pressure of pure solvent, they have given 1020 and of its solution is 990 divided by 1020. This I have to teach you, but anyways, we will see. What is the smaller W? 5 grams of solute, 5 into molecular mass of benzene. What's the molecular mass of benzene? The molecular weight of benzene is 78. You should know how to calculate C6H6. So 12 into 6 plus 1 into 6. So 78 is the molecular mass of benzene. Divided by, we need to calculate the molecular weight of the solute. We don't know what is the solute. They have just given 5 grams of solute is dissolved. And what is W? They have given the amount of benzene, 58.5. See, this representation is not clear. I'll teach you the representation. So on solving for m, you will get m to be 220. You will get m to be 220. So answer for this question is option A. Option A. This I will have to teach you. This is called as Oswald's Walker's method. So this formula is based on Oswald's Walker's. We will derive this. We will derive it in the next class because it's already time, right? So we'll derive this formula in the next class, and then we'll continue with the other parts of the topic. So few problems. There are more number of problems to work. Anyways, we'll work later. I hope these problems and relative lowering of paper pressure is clear for you. Yes? Yeah. Yeah. So we'll continue the class next Tuesday. Next week we'll continue the class. All right, ma'am. I'll stop the class, ma'am. Ma'am, I'll stop the class.
Yes, sir.
Yeah.